So, ladies and gentlemen, you should be in your textbook, page 458. On that page, you will find this exact same chart. I just wanted you to have it in front of you because it's kind of hard to read up here. Okay? So, let's just recap a little bit. Okay, because I realize, we've had a number of days where I haven't seen you. We talked about the big topic that we covered at the beginning of chapter 10 was intermolecular forces. Okay, so let's just recap about that a little bit. Tell me first, what does the prefix inter mean? Between. Okay, there's intermolecular forces, and what's the other prefix we talked about? Intra, which means within. Good, okay. So within a compound, what's holding atoms together? There are two types of intra bonds. What are the two types? Ionic and covalent, okay. Inter means between, okay? Let's review that a little bit. All right, there were three types of intermolecular forces. Do you remember which of the three was the weakest one? London dispersion, okay? What's next in order? Dipole, and the strongest of the three? Hydrogen bonding, okay? Now, what I'm going to ask you to do in just a minute is I'm going to give you a list of compounds and elements, and I'm going to ask you to classify them. Tell me what type of solid these substances form. And that's what this chart is good for, okay? It shows you the classifications of solids, okay? And we're gonna look at this chart in reverse order. We're gonna read it from right to left. So what I'm gonna ask you to do on the next slide, there's a whole bunch of elements and compounds. The first thing you decide is it an element or a compound? Okay. Well, let's say it's a compound. What are the two types of compounds out there? Ionic and covalent. Okay. How do you know if something is ionic or covalent? Okay, if it's a metal and a nonmetal, it's ionic. A covalent is made up of two or more nonmetals. Okay, so let's say you come across a compound, you decide it's ionic. Well, clever name I know, you would say it is an ionic solid. All right, now let's just review a little bit. We covered this at the beginning of the chapter. What holds an ionic compound together? Like a chunk of salt, a big block of salt. What's causing it to stay together? Yes, sir. Okay, what's holding the pieces of the crystal lattice structure together? Okay, and what is an ionic bond? Okay, correct. When one atom takes electrons away from another, or they're given, it's that attraction from opposite charges. I used a really fancy word. I said, or fancy term. I called it the electrostatic attraction. That just means opposite charges attract. And folks, that is an incredibly strong force of attraction. Okay? And if something is held together really, really, really tightly, okay, it doesn't easily come apart. It doesn't easily melt. Remember I asked you the question, have any of you ever seen liquid table salt? And what did you say? No, why not? How come we haven't seen that? Incredibly high melting temperature. Why is it so high? Because ionic compounds are held so tightly together. Okay? Very hard, very brittle, very high melting points. Excellent insulators. What does it mean to be an insulator? Yeah. Okay. Does not conduct heat or what else? electricity. And we looked at some structures as to why something is an insulator versus a conductor. If something is held very tightly together, there's no room for electrons to move around. So it's an insulator. Okay? So let's say you've got a compound. This time it's not ionic, it's covalent. You don't call it a covalent solid, you call it a molecular solid. Okay? Remember, the word molecular in your mind should mean covalent. Okay? These are the ones that are held together, not with opposite charges. There are no charges here. What holds a molecular solid together? Nope. That's what holds the molecule together. What holds this molecule and this molecule together? Intermolecular forces. Yeah. Dipole-dipole, London dispersion forces, hydrogen bonding. Okay? And guys, if I give you a molecular solid, I'm going to expect you to be able to tell me which intermolecular forces are at play here. Okay? Let's keep moving. Let's say it's not a compound at all. It's a pure element. Then it's going to fall into one of these categories. Okay? It's an atomic solid, and there are 3 types. The first one here, it says group 8A. Ladies and gentlemen, group 8A is another way to say group 18. What is the name of the family of elements in group 18? Noble gases. Okay, now I know what you're thinking. Noble gases. Solids. What? Well, no matter what state of matter any element is at room temperature, it can be made into a solid if you cool it down enough. I mean, there is such a thing as solid oxygen. Okay, it's not impossible. You just have to be at a really, really low temperature. If it's a metal, again, clever name, you call it a metallic solid. And then there is this third category. They're called network solids. And ladies and gentlemen, you're given one example. There are 2 more that I want you to write down. So the one given to you is carbon diamond. Diamond is what element? I just said it. Carbon. Yeah, pure carbon. Carbon diamond is a network solid. Here are 2 more that I want you to know. The element silicon is a network solid. A lot of your parts in your computers are made of silicon. Okay? Here is another one, and I realize what I'm about to write is not a pure element. It is a compound. It's one of these weird exceptions. This is another network solid. Silicon dioxide. Do any of you know the more common name for silicon dioxide? Do you know it? What is this? What is it? Quartz. Okay. Silicon dioxide is quartz. All right. When quartz is ground up into a very, very fine powder, do you know where you see it? At the beach. Sand. Okay. Sand is essentially ground up quartz. I mean, it's other things. It's got ground up shells and other things, but it is primarily silicon dioxide. That's also one of the components of glass as well. Okay? But when glass is not a network solid, okay? Silicon dioxide, when it's in its quartz form, is a network solid. And ladies and gentlemen, here's what I want you to know about a network solid. These are the most, this is poor grammar here, the most tightly held solids on this chart, even tighter than ionics. Remember we said diamond was the hardest natural substance on Earth? Okay? It also has one of the highest melting points. So does silicon dioxide. Okay? Extremely, extremely strong bonds holding it together. All right? And, you know, think about it. Have you ever seen a beach melt away? No, I haven't. There is a sort of interesting phenomenon that happens if there is a lightning strike ever on a beach, okay? A lightning bolt contains enough heat, enough energy to very briefly melt the silicon dioxide, but then it's so quick that it re-solidifies again, and you get these really, really interesting formations. It's sort of like glass. Anyway, you should Google it. It's interesting. So, let me tell you guys, this material is pretty much going to be covered all in multiple choice. There are very few free response questions that are going to ask things to do with this categorization. So here's what I want you to do. You've got a list of substances here. First thing I want you to do is tell me, what type of solid is it? Is it an ionic solid, a molecular solid, metallic solid, network solid? What is it? If, and only if it is a molecular solid, which means it is what type of compound? Covalent. If it's covalent, I want you to also tell me what intermolecular forces are at play here. Go. Do science. So, let me make sure something is clear. A couple of people were asking me about this. If a compound is covalent, all covalent compounds have London dispersion forces. All of them. If it is a nonpolar molecule, then what? Then that's all it has. Yeah, then it has London dispersion only. If, however, it is a polar molecule, it has London dispersion, and it also would have what? Dipole-dipole, and it might also have hydrogen bonding. Okay? I would strongly suggest go back and review how you tell when something has hydrogen bonding and when it doesn't. Okay? Because not everything that has hydrogen bonding. Okay? So this is primarily going to be on multiple choice. You know, the following element is classified as what type of solid. Okay? Simple. So we are going to change gears here a little bit. The last section in this chapter moves away from how are solids and liquids held together and starts talking about the interaction between phases of matter. When a solid turns into a liquid, when a liquid turns into a gas. Why is this in this chapter? Because these phase changes occur or are affected by the strength of intermolecular forces. Okay? So we're going to talk about vaporization, evaporation. There is some overlap between this chapter and chapter 6, which I'm sure you don't remember, but that was the chapter on heat, energy, thermochemistry. Okay? there's a little bit of overlap because we are going to be doing some heat calculations, okay? Why? Again, because these phase changes involve either breaking or forming intermolecular forces, right? Now, okay, when we started this chapter, I gave you a couple examples of free response questions, like, here's two compounds, which one would have the higher melting point? Or which one would have the higher boiling point? And you made that decision based upon the strength of the intermolecular forces. Let's just review for a second here. If I put a pot of water on the stove, and I turn the heat way up and it starts to boil and we see vapors coming out of the pot, if it's a pot of water, what's in the vapor that's coming off?
Water.
Water. It's water vapor. Why do I keep bringing up this example? Because I want to make sure you understand that phase changes are breaking intermolecular forces, not intra. If you put a pot of water on the stove and boiling it means breaking intra, what would be in the gas? Hydrogen and oxygen. And that's not what's happening. Okay? So we're going to talk about another concept here. And you're going to have very similar free response questions. Here's two compounds. Which one has the greater vapor pressure? Okay. Well, we've talked about that concept back in our gas laws chapter. Vapor just means gas, and gases exert pressures. Okay. Before we talk about this relationship, I want to introduce you to a very important vocabulary word right here. Volatile. Or volatile. Okay? Pretend that you're in your English class or you're taking an SAT.
Oh no.
And a person is described as having a volatile personality. What kind of person are we talking about? Angry? Give me some other adjectives.
Insane.
I don't like, no.
Excited.
High blood pressure.
High blood pressure. Okay?
Excited.
Yeah, but excited in a negative way.
Easy to set off.
Easy to set off, short-tempered, gets angry quickly, okay? Does not think before they say things, okay? It means somebody who is very short-tempered, okay? Well, guys, the word volatile applies to this topic very well. In chemistry, volatile means a liquid that evaporates easily. Okay? Volatile liquids are liquids that evaporate very easily. No. Think about some liquids in your everyday life that have, an easy way to pick these out is ones that have very strong odors. Think of just things in your everyday life. Vinegar, rubbing alcohol. What else? How about what you put in your car? Gasoline. Okay, ladies, nail polish remover. Okay. All of these liquids that have a very strong odor have a strong odor because they turn into gas very easily. And that's what you're inhaling or smelling, okay? And back in our chemical storeroom, I have a cabinet, a metal cabinet that is called our volatiles cabinet. We keep all of our very volatile liquids in that cabinet because it's a fireproof cabinet. Volatile liquids are also very flammable. And think about it. Alcohol is definitely flammable. Gasoline, definitely flammable.
Oh,
Okay? Do you all know what the main component in nail polish remover is? Acetone, flammable. Okay? Now, let's look at how it's defined here. If something evaporates easily, that means it turns into a gas easily. Lots of gas is going to exert lots of pressure. Volatile liquids are liquids with high vapor pressures. Okay? And think about this logically, ladies and gentlemen. If my hands represent two liquid particles that are held together, if these two easily pull apart to form a gas, are they held loosely or tightly together? Loosely. So think about it. If you have intermolecular forces that are high, or another way to say that is very strong, they're not going to easily be pulled apart. So if they're not easily pulled apart, we're not getting as much gas. If there's not as much gas, there's not going to be as much pressure. It is an inverse relationship. The stronger the intermolecular force, the lower the vapor pressure. Okay? So let's do an example. We had these two compounds just on the last slide. Methane versus water. Let's say it's a free response question, and I ask you, which one of these has the greater vapor pressure? Okay, now don't answer immediately. Here's the process I want you to go through. I want you to think, okay, high vapor pressure. That means lots of vapor, lots of gas, which must mean easy to turn into a gas. Is that strong or weak intermolecular force? Weak. Okay? The next step would then be to tell me specifically what intermolecular forces each compound has. What does this one have? London dispersion only. How about this one? All three. All three. This is held so tightly together. And Xander, this is answering your question. This is why water is not a volatile liquid, because it's held very tightly together. So what's the answer? Which one has the higher vapor pressure? This one. Okay? So most of your non-polar liquids are volatile. They're flammable. Okay? Not things that you want to have hanging around in mass quantities. Okay? And there's a relationship with temperature as well, which I'll talk about in a second. Okay? This is a very crude demonstration of what piece of equipment? A barometer. And I want you to focus on this blue one and this sort of orange one. Okay? This is water. We just saw this example. It's got London dispersion, dipole, and hydrogen bonding. Okay? This compound right here, if I drew it out, you'd be able to see that it is polar, but it doesn't have hydrogen bonding. So it's got London dispersion and dipole, but it does not have hydrogen bonding. Look at the numbers. Look at the effect that changing the intermolecular forces has. Water, which has all three, in this diagram, or this picture, has a vapor pressure of 24 torr. When you lose hydrogen bonding, it jumps up to 545 torr. Can you imagine what kind of vapor pressure we'd be looking at if it was a molecule that had LDF only? It'd be in the thousands. Okay? Because they're compounds that evaporate very easily and form a lot of gas. Okay? Let's talk temperature. Okay, don't worry so much about this diagram. What I really care about is this relationship right here. Well, guys, this should make sense to you. Tell me first, if you raise the temperature of anything, solid, liquid, gas, I don't care what it is, what are you physically doing to the particles? Agitating them, making them move faster and with more energy. If two particles are now moving faster with more energy, do you think that they can pull apart more easily? Yes, they can. If you raise the temperature, you will raise the vapor pressure. That's a direct relationship. Okay, are you ready for some good news? Here is one of these changes from last year to this year. This is an equation that is not on your equation sheet that we will not be using. Okay? Essentially, this equation is simply showing you the relationship between temperature and vapor pressure. Was it direct or indirect? Direct. Okay. Last year and years previously, we graphed this equation and we got numbers off of a graph. And the point is, you could use this to solve. Given a temperature, you could actually solve for the vapor pressure of that liquid at that temperature. Okay. We are not going to use it, but I wanted to just show it to you. Okay. Those questions that I took out of the problem set use this equation. Okay. So, we're going to talk about all the phase changes. Melting. We'll be talking about the heat of fusion. Remember, that means that's a number that you can use between solid to liquid or liquid to solid. It doesn't matter. And we'll talk about boiling as well. I wanted to make sure you are aware of this relationship. Okay, I briefly mentioned this when we were in the gas laws chapter, but I want to just mention it again. Have you all ever noticed that if you're heating something up, whether it's here on a hot plate or at home, you're boiling water, whatever, have you ever noticed that before the boiling gets going, you get these little tiny bubbles on the bottom of your container, and eventually they break free and go to the surface? Okay? Let's say you're heating up a pot of water. What's in those little bubbles? What kind of gas? What gas? Not oxygen. Water vapor. Okay? Well, ladies and gentlemen, boiling will not occur until the pressure of the gas in those bubbles is equal to the pressure in the room. When you've added enough heat to that pot of liquid, whatever it is, that the pressure of the gas in those bubbles is equal to the pressure in the room, that is when boiling will occur. Now, at Oakton, okay, we are not at sea level. Oakton is at about approximately 300 feet above sea level, that elevation. As you go above sea level, the standard pressure starts going below 1 atmosphere. So at sea level, standard pressure is 1 atm. Because we are a little bit above sea level, what would be considered our normal pressure might be like 0.98 atmospheres. Okay, well, let's take this to an extreme. You're at the top of Mount Everest. Good for you. Okay? When you are at such a high altitude, the pressure in that air is much lower than it is here. If the pressure is lower, and let's say you're camping out and you're heating up a pot of water, okay, you can get the water to boiling, but if you were monitoring the temperature of that water, water might boil at like 75 degrees on Mount Everest. Okay? It's boiling, you could put your hand in it and it wouldn't burn you. Okay? Why? If there's a lower pressure in the surrounding atmosphere, that means you don't have to add as much heat to your water to get it to boil. Okay? For any of you that do any kind of cooking or baking, have you ever noticed on the instructions it'll say, do something different for higher altitudes? Have you ever seen that? Okay, well next time you're cooking or baking something, not for everything, but particularly like when you're baking a cake or muffins or something like that, they'll have an alternate set of directions. think about it. Let's say you're cooking pasta up on Mount Everest. Pasta party! Okay. You know, your water starts to boil, you throw your pasta in there, but the water's only at 75 degrees. What does that mean in terms of your cooking? It's going to happen, but it's going to take longer. So if you'll notice, sometimes the directions for at higher altitudes will either have you cook something for longer, or they'll have you set your oven to a slightly higher temperature. Okay? And the opposite would be true. Okay? Now, it's not a huge difference, but let's say you were in somewhere below sea level. Like some of the city of New Orleans is technically below sea level. Okay? The opposite would be true. Do any of you, have you ever used a pressure cooker or seen a pressure cooker in someone's kitchen? Okay? So you put something in there, you close the lid, you crank it down. What that does is make basically like an environment inside the pot that is at a higher pressure than what the room is. So if this room right now is at like 0.98, maybe I can turn my pressure cooker on and make the environment inside that pot at like 1.5 atmospheres. If you increase the pressure, water's going to boil at a slightly higher temperature above 100. So what's the purpose of a pressure cooker? What's the benefit? Why would that be a good thing? Yeah, it cooks faster because it's at a higher temperature. Okay. Anyway, I just wanted to make sure you guys were aware of that fact. Okay, so your location changes how things boil. Okay, and if you're doing boiling, we're talking about H-vape, heat of vaporization. Does this look familiar to you?
No.
Boo! I kind of like it, but I'm in the minority, I'm sure. Ladies and gentlemen, this is a heating curve, which you did in Chem 1. Now, please understand why this is in this chapter. Why wasn't this back in chapter 6? Because it wasn't. This is here because phase changes are involved, and phase changes involve breaking intermolecular forces. So it gets lumped in this chapter. What I want to do before we do a sample problem is just review this curve with you and make sure you understand what's happening at every point. Okay? Temperature is on the y-axis. I think time is on the x. X doesn't really matter. Okay? But I'm basically heating a sample of water through different phases. What I want you to tell me is what state of matter exists at different points along the curve. And some of it is written here, but we're going to go into more detail. So let's start down here. Negative 20 degrees, this little red dot right here. Solid. Okay, fine. Now I'm going to start to raise the temperature. I'm raising it, I'm raising it, I'm raising it, I'm raising it. I'm up to 0. What state of matter am I at this dot right here? Melting is not a state of matter.
Solid and liquid.
Not solid and liquid. Solid. 100% solid. Now what's happening as I move across?
Solid and liquid.
Okay. I'm melting. Melting, 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 melting. What state of matter would I be at this dot?
Liquid.
All liquid. And the temperature stays constant until all of that solid is melted. All right, now we're going to heat up, heat up, heat up, heat up, heat up, heat up, heat up. Heat up. What am I at this dot?
Liquid.
Liquid. What's happening from this dot to this dot? Vaporization. So what state of matter am I here?
Gas.
Gas. And then all up in this region?
Gas.
Yes. Okay. So what this curve is good for is calculating a change in energy over some period like this, okay? I want you to tell me, because this is back from Chem 1, so let's review. What equation do you use at each part? If I asked you to do a calculation somewhere on these slanted parts, do you remember what equation to use? MCAT. What does Q represent? Heat. What's M? Mass. C is specific heat, and delta T? Change in temperature. Very good. Okay. What about the flat parts? Tell me first, why is it not appropriate to use this equation on the flat parts? There is no change in temperature. Delta T would be 0 all the time. But you can calculate the heat required to melt a block of ice. Do you remember what to do?
Oh, I was actually going to ask you a question. What is the x-axis of that?
I think it's time. It doesn't actually really matter. The y-axis is what I care about. How do you calculate a heat on these flat parts? Does anybody remember? Okay. So this bottom one would be, I'm going to say Q equals amount times the heat of fusion. I say amount because sometimes it's a mass in grams, sometimes it's an amount of moles. Depends on the problem. What would you do up on this top line? Yeah, same thing except heat of vaporization. Okay? So what I'm going to do to refresh your memory on this is I'm going to go through a sample problem with you, and then I'm going to have you do one on your own. Okay? This looks like a long problem. It's actually not. It says calculate the amount of energy in kilojoules needed to heat a certain amount of liquid water. I'm going to underline that because that's going to be important later on. From 0 to 182 degrees. And then I'm given a whole bunch of extra information. My suggestion to you in a problem like this is draw a quick sketch of that heating curve. Figure out where you're starting and where you are ending. If this is water, what temperature is represented by this lower line? Okay, 0. And the upper line? 100. Okay? It says we're starting at 0. Where on this line should I draw a little dot marking where I'm beginning?
To the right, because it's
Why?
liquid water.
It says it's liquid. If it said solid, then I would be on the left. I'm going to heat up to 182. Well, that's somewhere above this line. I'm just going to put a little X there. Guess how many steps this problem is? Yep. 1, 2, 3. Okay. So here we go. What equation am I going to use for step 1? MCAT. MC delta T. Which specific heat capacity should I use? There's 2 of them given to me. Okay, because that's the one over the liquid range. Be careful. What's the delta T? It is not 182. 100. It's just the change from this point to this point. 100 degrees. Okay? I'll save you the time. You multiply that out. You get approximately this. They wanted our answer in kilojoules. Let's go ahead and convert that. Okay? How do you do step 2? Okay, so amount times the heat of what? Not fusion, vaporization. Now guys, this is why I said amount. Look at the heat of vaporization we're given. It has moles down there. Was I given moles of water? No, but you could get it. 346 divided by 18 gives you 19.2 moles. Times that. Okay, I will tell you, sometimes heats of fusion and vaporization are in something per mole, sometimes they're per gram. If this was given per gram, then I wouldn't have had to make this change. Last part. It's another slant, so I'm doing MCAT again. And it's in the vapor phase, so I don't want to use 4.18. I'm using this one. What's the delta T? 82. Change to kilojoules. What do I do now? Add them all up. All right. Now, I want to tell you something about this problem. I wouldn't give you a problem like this on a test. Too easy. So why did we do this? Because you need to be familiar with this process, because this process will be part of a larger problem. Like this one. Okay? Here we go. I'm going to introduce you to it, and then you're going to do it on your own. Actually, some really interesting real-life application here. It says, compounds like CCl2F2 are known as chlorofluorocarbons, CFCs. You may have heard of that term when you read something about depletion of the ozone layer. They are bad for the environment. Okay? Why were CFCs used so much years and years ago? Because they are excellent refrigerants. They are used in refrigeration, or they used to be. Air conditioning units, refrigerators, freezers, etc. Okay? You're given some information about this CFC, and here's what you're being asked to do. The question says, what mass of this substance, meaning this one, what mass of this CFC is required to evaporate, or what mass of this substance must evaporate in order to freeze a sample of water that's at 15 degrees. Now, let's just stop writing anything down. Don't calculate anything yet. Just let's think about this. If water is at 15 degrees, what state of matter is it? Liquid. Liquid. Okay? If you want to freeze it, what do you have to do? Cool it down to what? 0. Okay? Cool it down to 0 and freeze it. Well, tell me this. if we are trying to freeze the water but evaporate means liquid to gas, this guy, tell me this. We're going to break this into pieces. If you are going from a liquid to a gas, is that an endo or exothermic process? Liquid to gas, does that require energy or will it put energy out? It requires it. It's not going to happen unless something else provides energy to it. It's endo. Where is this energy going to come from? You can't just pull it out of thin air. Where is that? Think about it. On our refrigerator, are you putting any heat into our refrigerator? No. So where's that heat coming from? Not electricity. Look at the last part here. Think about it. Think about it. The water goes from 15 degrees down to 0 and freezes. Doesn't that sound like you're taking heat away from that water? Yeah. Where's it going? It's going to heat this guy. That's how refrigeration works. You put something at room temperature that you had for dinner into your refrigerator. Your smart little refrigerator pulls heat from that fried chicken or whatever and uses it to do some other process. Now, I don't know this for sure, but I don't believe compounds like this are used anymore because they are harmful to the environment. But here's the gist. The heat released from the water is equal to the heat gained by the CFC. Let me say that again. However much heat was lost from the water cooling down and freezing will be gained by the CFC. Here's where I think you should start, and then I'm going to let you go. My suggestion would be to draw out that stair-step heating curve. Figure out where you are starting with this water at 15 degrees that is to be cooled and frozen. Where are you starting? Where are you ending? You have all the information you need to first calculate how much energy will be lost by the water. Start there. Okay? type of problem you should be prepared to see whenever our next test is. I don't know when it will be. Remember that, guys, I'm combining chapters 10 and 11. So that's why I don't know when our next test is. Okay? So that's it. That's the end of the chapter.